Okay, so yes, it is also very effective. It has two versions, at least. One is based upon energy, based on energy, and second is based on Galerkin method. So finite element method actually stems from Galerkin method, one of its versions. There are two main versions. One is based on energy and the other on Galerkin method. So from that point of view, finite element method and Galerkin method are the same. That is just its more specific application. Any other questions? This, of course, Galerkin method can be done by hand, so to say. Finite element method can be done by hand if small amount of elements is used, say 2 elements, 1 element, 3 elements. But for bigger number of elements, already matrices become so big that we need computer applications. But here also the same thing happens for Galerkin method. If there is only one term approximation, it can be done by hand. Otherwise, we need also computer application. The same conclusion. Any other question? Can you repeat? I did not understand the question. Who do you? Student said that he's asking what he was thinking about, but who? Oh, I see. Student is asking me what Galerkin was thinking about. I don't know. Because that happened in 1915, and I was not around. I think you were not either. Okay, student is asking whether Galerkin was thinking about Newtonian or other approximations. I don't think that he had Newton's method of solving algebraic equations or other have no connection, of course, with Galerkin method, because Galerkin's method, say Newton-Raphson method, say it deals with approximate finding of the root of the equation, of some equation, algebraic equation or any other equation. Here, Galerkin wants to solve the differential equation. So this is much more difficult a task than solving, so to say, algebraic or any transcendental equation by. So what student is referring to, I think, is as follows. 11. Imagine I have this equation, f of x equals 0. And this f of x is like this. And I would like to find this root. So I would like to find x0 such that f of x0 equals 0. Okay, and that is f of x. Okay, sometimes we are approximating it like this. We take these 2 points, and then we pass a line between these 2 points. So then this is first approximation of the root. But then we are calculating function at this point. So this, naturally, as we see, does not coincide with the root. So then we actually calculate the function at this point. If the function is negative, then we again pass the straight line between here and the other point. Then this will be a second approximation of the root, etc. And this process continues, and this process is converging to the root. So that is the root. So that is Newton's method. But this Newton's method is not connected, as we see, with Galerkin's method, because Galerkin is interested with solving differential equations, much more difficult a task, rather than solving. Newton, as far as I know, never formulated the differential equation. He developed differential calculus, how to differentiate, how to integrate. Euler was the one who wrote first differential equations and solved them. So Newton and Galerkin are totally in different, so to say, fields. The only thing is that sometimes when we are using many term approximations, final solution can be solved by Newton's method. So that then we need both Galerkin's method and Newton's method. Any other questions? Please continue to ask questions, because asking questions allows us as if to stop somewhat, but then to reflect of what we are doing, where are we going, etc. So it has a very useful purpose on top of answering them. Okay, then what the questions that we will be posing is 27, topic 27. How to construct approximating functions. Or approximating function psi1. So that is a question. Any ideas? Any ideas how to construct these approximating functions? How to construct the functions. Okay, one of the suggested answer is that functions psi1 should be related to mode shapes. Okay, actually, so that is a comment. Psi1 is an approximation of the mode shape. So mode shape, what does it do? Mode shape satisfies boundary conditions and it satisfies differential equation. Psi1 satisfies boundary conditions. Does not necessarily satisfy a differential equation. So that is a correlation, so to say, between mode shapes and psi1. Mode shape satisfies both boundary conditions and governing differential equation. Psi1 satisfies boundary conditions, but not necessarily the differential equations. That is why it is an approximation. Had it satisfied both, then it would be an exact solution. if psi 1 satisfies boundary conditions and governing differential equations, then we are very happy. We have hit exact solution. The greatness of Galerkin's method is that you don't have to hit the exact solution. Still, it's very great approximation. So that is very beautiful.